Dr. Julian Henn, who is the CIO of the Data Q intelligence company. And Julian, between 1993 to 2000, studied physics at the Julius Maximilians University, Würzburg, Germany, finishing his studies with university diploma degree. After a short research stay at Chalmers University of Technology, Göteborg, Sweden, he did his PhD in theoretical chemistry at the University of Würzburg from 2001 to 2004 with the doctoral fellowship founded by the Deutsche Forschungsgemeinschaft and finished this with summa cum laude. Congratulations, Julian. Well, he worked then from 2005 to 2006 as a Fedor Linen Research Fellow of the German Alexander von Humboldt Stiftung at the School of Physics and Astronomy at the University of St Andrews, Scotland, in a theoretical quantum optics research group. In 2006, Julian switched to the George August University Göttingen, of course, Germany, where he started developing feed quality indicators. In 2010, he moved to Bayreuth, probably because of Wagner music.
No.
For embarking on habilitation in physics founded by DFG at the Bayreuth University. He finished his habilitation in natural sciences in 2016 with the topic quality indicators for feed data with applications in crystallography under the supervision of Professor Peter Luger. In 2016 and 2021, Julian came to our group, and Julian was staying firstly for 3 months, then for half a year as a guest professor in our group. That was very interesting period. I mean, unfortunately, the second period was outbreak of pandemic, and it wasn't that effective as it could have been. But still, we had plenty of interesting discussions, and Julian gave a series of excellent lectures, very well attended in our group. And Julian started his company, Data Q Intelligence, founded in 2022 together with Sławomir Domagała, formerly in our group, and Patrick Newt. And this company provides innovative metrics and data quality protocols, as well as workshop and consulting. In his spare time, Julian likes to be in nature, to be out in nature with friends and for hiking, rock bouldering, and sport climbing. So, Julian, very welcome. The screen is.
So thank you very much for this very nice introduction. And thank you also very much, Professor Wojniak and Professor Dominiak, for the invitation. And first of all, I'd like to say hello, particular to all guys at Warsaw University who I know. I saw some of you in the chat. So here's a hello from me, and of course also to all others participating in the audience. Yes, I'm talking to you today about data quality topics, and first of all, I need to say that I speak on behalf of Data Q Intelligence, and as Professor Wojniak just mentioned, Sławomir Domagała, who is well known in Warsaw University, is a founder of our company. Patrick Nord is our economist, and and I'm the third guy in this. So what we aim at is to push the topic of data quality in diffraction experiments, in X-ray diffraction experiments mainly, but also neutron diffraction experiments, for example. And we want to raise the quality and the standard and reach a point where certification of the data is possible, so that it's easy to say these are, for example, data of the highest standard, and these are data good enough for publication, and to really discriminate well between those. Because as we will see also in this talk, there is a large spectrum of quality out there, and all of them are published. So so today I'm talking about the global indicators and filtering system. So what's a global indicator for data quality? It's that single number which gives you an entire picture of the whole data quality. And when I refer to data quality here, I mean I always refer to systematic errors or systematic improvements. So it's not just the observed intensity, it's always the comparison between observed intensity and calculated intensity. So we are also very happy when calculated intensities are also deposited and made available, because we are working with those with those calculated intensities. So the global indicator would be the one number which gives you overall insight into this into the data quality of your data set. And the bad news is that's actually not possible. It's not really possible, because with diffraction data, we have always at least a dual space. So we need to take into account different views. And even if we concentrate on just one space, on reciprocal space, for example, even then it's better to have several indicators and to combine them in a meaningful way. And a meaningful way this could be combined to would be a filtering system. A filtering system where you have to pass several tests in order to come out positive at the end. And if one of the tests fails, you know something is there to do. And I'm going to talk about both of them today. First of all, I want to talk about the R factor gap in small molecules crystallography. And that's actually the first time we present that. It's not even published. You are the first one to hear about that. And it's intended to be one of those kind of global indicators, in that sense that if we evaluate the R factor gap for small molecules crystallography for a large number of data sets from a crystallographic data bank, for example, then we get an insight into how the data quality is approximately the overall data quality for a large number of data sets. So what's the R factor gap in small molecules crystallography? The R factor gap is actually was invented by Holton et al. Oh, sorry. And comes from macromolecular crystallography, and was developed there first and is established there as well. It's the difference between in macromolecular crystallography, it's the difference between the internal R factor and the external R factor. And in small molecules crystallography, we will define it a little bit different as the ratio between the actual R factor, that's what you get from your refinement, and the best possible R factor given your data. So let's make this a little bit more concrete. The best possible R factor, what is that actually? It's the predicted agreement factor under certain assumptions, which we don't have the time to go into today, all of them. Let it put me in that way. If there's no systematic error at all in the data and in the model, systematic error is always in the model actually, but that's a different story. So if there's no systematic error at all, you could you can give a predicted agreement factor which refers to this situation. No systematic error at all, which of course includes that all standard uncertainties in your reflection file are accurate and valid, and also the observed intensities and so on. So we define the R factor gap in small molecules crystallography as the ratio between the R factor from your refinement divided by the predicted agreement factor. So under ideal circumstances, the R factor gap is just 1, and that means there is no R factor gap. If it's 2 or 3, that means your agreement factor from your refinement is double or three times the best possible value. Okay, now what we did is to apply this concept to a large number of data sets. We applied it to all datasets published with IUCR data between 2020 and 2022, apart from a few where we had either missing information, like when the calculated intensities were not given, or when there were exotic weighting schemes which we cannot deal with yet. So if we take this away, that were like 10 to 15 data sets which we had problems with, or where no calculated intensities given, but the resulting number is still large. It's 310 data sets from publications with IUCR data between 2020 and 2022. So what we did is to calculate this R factor gap for small molecules crystallography. And this is depicted in this slide. How the distribution looks like. It's not the distribution itself, it's the cumulative distribution. That's sometimes easier to interpret and nicer to look at. So what you see here is this cumulative distribution of the R factor gap for small molecules crystallography. On the x-axis, you have this factor x, which is this ratio between actual agreement factor and the predicted one, so the R factor gap. And on the y-axis, you have the cumulative number of data sets with a value of the R factor gap below that value, where you are actually on the x-axis. So what does this mean? If we look at this, we see the median is 3.33. So this means in small molecule crystallography, we have like 50% of all data sets have an R factor, which is 3.33 times as large as the best possible one. So we do have in small molecules crystallography an R factor gap, and it's actually quite large. We lose a lot of information under these assumptions made, which we don't have the time to go into detail today. The average value of this R factor gap is 4.13. So on average, the R factor from small molecules crystallography is 4 times as large as it could actually be. I hope you are shocked a little bit, at least, because small molecules crystallography is assumed to be much more accurate than, for example, macromolecular crystallography. And in this publication where the R factor gap was established, they even state in small molecules crystallography, there is not such a thing as an R factor gap, because the calculated intensities are assumed to be much more accurate than the observed ones. So I'd like to object here that not everything is as good as it looks like from a viewpoint of macromolecular crystallography when you look at small molecules crystallography. So this was one example of kind of global indicator. I give you another example, which we also didn't publish yet, but which is a very simple concept, easy to grasp, and very easy, particularly for any crystallographer, because we're dealing with these kinds of entities all the time. So after doing the refinement, you get a set of weighted residuals, and this set of residuals should be centered around 0. This means it should be symmetric with respect to positive and negative values. Even if it's not a Gaussian distribution, it should be symmetric. And you can calculate the mean value of your whole set of weighted residuals, and then this mean value should be centered around 0, as I just said. But it can vary, of course, due to statistical fluctuations. And this range of statistical fluctuations can be easily calculated. And then if you calculate this, you can also say whether the mean value of weighted residuals is inside statistical fluctuations or outside. So similar to concept of observed intensities, we define here that that if the significance of the mean value of the weighted residuals is between -3 and +3, then it's assumed that this is within statistical fluctuations, and if it's outside that range, it's assumed to be not consistent with statistical fluctuations anymore, in particularly when it's far outside. So how does that look like now if we apply that to these 310 data sets from IOCR published with IOCR data in the years 2020 to 2022? It looks like that. We have this time the distribution itself, not the cumulative distribution depicted here. And you see the 0 is here in the middle, and the range -3 and 2, 3 is depicted here with these dashed red lines. And the solid red line gives again the median. The median is 1.94. So we have, on average, that the mean value of the residuals is shifted towards slightly positive values. But you see that this distribution extends over a large range. So outside of this range are 56% of all these data sets from this 310. So we have the majority of data sets outside of this range. Let me show you another indicator which is similar but not exactly the same. If we don't look at the residuals themselves, but just at their sign, which can be +1 or -1, and add these signs up, we get what's called a random walk. And if these residuals have the same probability for positive and negative signs, this random walk will not lead far away from the origin. And the standard deviation for this can again be given with a sigma value, which is the square root of the participating number of participating reflections. So that's actually similar to the residuals, but it's not the residual values itself like before, but just their sign, the sign. So how does that look like if we apply it to 310 data sets published with IOCR data? We are just preparing this publication at the moment. It looks similar to the picture before. We have like a distribution which is slightly shifted towards positive values. The median is 1.39. So we have one standard deviation shifted to the positive region in 50% of all the cases, and or larger. And outside of this range would be 54% of all data sets. So again, the majority of data sets doesn't fit into this range, which is deemed to be in accordance with statistical fluctuations. So if we now combine these two metrics and plot the data, it looks like that. So we have on the x-axis here the mean value of the residuals over the standard deviation of the mean value of the residuals. And on the y-axis, we have this random walk concept. Actually, it's the sigma value, the standard deviation, the excess residuals divided by the standard deviation. So both of these quantities should be within a limit of -3 to +3. And these limits are depicted here with dashed lines again. So what you see here is that those two entities, they are correlated, of course. They describe something similar, but not exactly the same, because if they would describe exactly the same, they would be on an exact line. And if we look now for those data sets which are inside the range between -3 and +3, it's just 33%. Just 1/3 of all data sets is within this range. Excuse me. So what we have done here is actually we have developed a kind of filter system by applying two slightly different criteria and then combining them, and then we can get these nice pictures here and see how they are connected. And we also see that despite that they are describing something similar, they are not completely dependent on each other. So we have in both directions here some scattering. So, and in this way, we could now go on and define further and other criteria, and also base them on statistics, so that we have a range which we can apply, which is related to confidence interval. And in this way, if we do that consistently, we get a filtering system or a data quality grid, or we call it just a color code card, because it looks like a color code. So today we have just very brief time. I can't go into the details. I would love to do that, but I can't. So I need to be short with this. So what you see here is a grid of green, yellow, and red cards. And if the card is green, this means the numbers are in a range which is consistent with statistical fluctuations. If it's yellow, it means that these numbers are just outside the range of statistical fluctuations. And if it's red, it means it's far outside this range of statistical fluctuations. And the whole card is built in a certain way, which I can very briefly just discuss here. So we have a block on the left side, which is to do with the squared weighted residuals. Sometimes I refer to this as the strength of the residuals. And on the right-hand side, we have the residuals themselves. And then we have in the first line of this card, the chi-square values from the Bacon plots, which some of you may know, particularly the guys from Warsaw. Then we have a line which deals with linear correlation coefficients, or to be more precise, with the significance of linear correlation coefficients. And then we have another line which deals with the significance of rank correlation coefficients. And then there are still other criteria which we can't go into today due to the time questions. And then we have, additionally to these horizontal lines, we have also vertical bars. So this is organized in a way also to have consistently the same properties in each column. And these properties are the intensity, the standard deviation, the significance of the reflection, and the resolution for both blocks of the squared residuals on the left and of the residuals on the right. So what can you do with something like that? And how do you apply it? I have a nice example for you. If we go back to this kind of classical paper from the Wozniak group, at that time it was from Kaminsky and Domagala, who were at the Wozniak group at that time. It's one of those classical examples, oxalic acid, the standard structure, which is investigated over and over again. Of course, that's boring from a chemical point of view, but not from a point of view of reproducibility of results and so on, and also not from a standpoint of data quality. So what these guys did here, they had like 13 different data sets of oxalic acid from X-ray diffraction experiments and one data set from neutron diffraction experiment. And then they were looking for how consistent the parameters are and how much the model parameters are and how much they vary. And we can now have a look at the consistency of the data sets which were used in terms of data quality. How consistent were these data sets with respect to data quality by just looking at this color code card. And even if you don't know the exact content, but you know that it's based on statistics and confidence interval, you know that you can immediately see some patterns. So let's go to this and have a look at those 13 oxalic acid data sets from X-ray diffraction, and the 14th here, that's from the neutron diffraction. And what you can see immediately is that there are some data sets where only a few red cards are there. For example, for oxalic acid number 4, it's just one red card. And for oxalic acid number 10, it's just 2 red cards. But then there are also others like oxalic acid number 11, where you see a lot of red fields, or oxalic acid number 13. And even the neutron diffraction set has a lot of red fields. So neutron diffraction actually has the reputation of being quite accurate. And I'm not sure whether this can be said with respect to these quality indicators. But what we see is that there are large differences between those data sets, and and I can say that already at this stage, this is valid also if we look for, say, for example, those data sets in IOCR, published with IOCR data. So how can we now take advantage of that? If you go back here to oxalic acid number 4, you see that in the 4th line, the 3rd field is red. And we have here an isolated error. Each red field is a systematic error. And this can be visualized. For each red field, you can also make a plot, or even different plots sometimes. And here, there would be an opportunity to go deeper into this oxalic acid number 4 dataset and examine why is this so much better than the others. That would be the first one, the first question. The second question is, can we find and remove this single systematic error? Because if there's just a single systematic error, it's of course much more easy to remove it than when you have, say, a collection of systematic errors, which all of them may interact also with each other. So that would be an opportunity. And then if you look more precisely, this field, which is red in oxalic acid number 4, this field, if we can remove it here, in all other sets, it's also either red or yellow. Oxalic acid number 9 is the only one where it's yellow. In all other cases, it's also red. So maybe if one finds this error and can remove it, this would also help to clarify the other data sets. And then if this could be removed, then in oxalic acid number 10, there would only be one red color left. And then we could do the same here. And in this way, one could use this to systematically improve the data and improve the models, not the data, of course. Data is just the data. How does that look like when we go to the publications with IOCR data? Here I give you the first 16 publications from 2022, and it's just this color card scheme. And again, we see that this kind of pattern repeats itself. We have some data sets with only few red cards, like this here, or also in the top right here. And then we have some some data sets where a lot of red fields appear, and all of them were publishable. So despite that there is a large discrepancy in the data quality, they are all passed the usual test. They are all publishable. And the difference in their quality is probably not very easy visible if you're not going into detail about the remaining systematic errors, or sometimes we call this also the opportunities for improvements. So, but also here, it could be interesting to focus on the best possible data sets from 3 years of publication with IOCR data. And going through all of these 310 data sets, we found these 4 data sets, which are the four best ones. So, of course, there's much more to say here. There are some more criteria which I can't go into detail as well, but we take it now as it is here. So we have like 2 data sets where not even a single red field appears, and then one data set where just a single red field appears, and then another data set with just 2 red fields, and all of them have at least 2 yellow fields. And also, this is very interesting because if you look at, for example, you can look at the diffractometer. You see that those 2 sets here are with a Rigaku diffractometer, and those 2 on the left side with Bruker. And then you can look for the share of diffractometers in this set of 310 data sets. And then these numbers come up. We see here this share of distributions of diffractometer sellers in this 310 sets. We see that Bruker has like a share of 58%, and Rigaku has a share of 15%. So they had a smaller chance to get in here. They occupy 50% of the best results. Of course, this must be taken with some caution. We should extend the number to look for that more precisely. That's just 4 data sets. That's not good statistics, but it may be interesting nevertheless, because it turns the attention to where we can look at and what we can investigate. It's also interesting to see that those 2 machines with Rigaku are actually from the same region. They come from Kazakhstan. It's not from the US or Europe, and those guys did somehow a really nice job. Okay, I rushed a little bit through this topic because I don't want to spend too much time or keep you away from your evening activities. So let's just summarize what we have talked about today. There is an R factor gap also in small molecules crystallography. People just don't know about it. They trust small molecules much more than they should actually. And we discussed 2 examples for this descriptors, the R factor gap and the mean value of the residuals, and then additionally the deviation of this random walk stuff. And then it was shown how this combination of requirements leads to a filtering system, reducing the number of data sets which actually pass all filters. And all of these descriptors which were used and which are presented in this color card scheme are based on statistics, and these statistics are based on confidence intervals. And if we apply those evaluation tools to, for example, data sets from one study like this oxalic acid study, we see that even in a relatively small number of data sets coming from the same laboratory, the data quality may vary quite a lot. And if we find out which one is the best one, we can finally put effort into looking more exactly what was done so well with this data set, what was missed with the other ones. And this can be done also for a large number of data sets, for example, for those published with IUCR data or from a data bank. We hope, and our aim is that in this way that the good data sets will get the attention they deserve, and that crystallographers who do extraordinary good work in their work, that this is given more attention and valid and more, how should I say, given more attention, and that those guys are probably also invited to publish about what they do and how they do it. So what makes data collection steps and data acquisition steps different in those cases? What do they systematically do better than in many other cases? Yeah, and in this way, and that's actually this closes the loop again. Our aim is to raise the data quality in crystallography in total, and to make data quality differences visible, and also opportunities for improvement. So if we apply this, we also facilitate learning about how to reach good data quality and to talk about it, to make it a topic, because by now it's more like every single group has its own way to do that, and also probably its own secrets, and that it's not so far, at least in my experience, not a topic which is really discussed in depth and wide across a community. We don't have a journal or a conference which deals just with systematic errors or with improvement possibilities in data acquisition, data processing steps. We may need to get there at some point, and if we do that for small molecules crystallography and then learn how to do this very accurately, this transfers also to charge density studies and maybe also to other fields like electron diffraction experiments. And with this, I want to close and thank you for your attention.
Thank you very much, Julian, for this beautiful lecture, and referring directly to our paper. So maybe are there any questions already? Yes. Yeah, there are several questions.
So the first one was from Kamil Dziubek.
Okay.
Let me read it. Thank you for your great talk, Julian. What do we exactly mean by the best possible R factor, defined as a benchmark in R factor gap? If using a different refinement procedure, we end up with different R factors, providing the same lattice parameter space, group atomic assignment, and weighting scheme. For example, OLEX2 comes with its own structure refinement programs, OLEX2.refine, but switching to shell XL under OLEX2 GUI, one can see small discrepancies. What's the reason behind this? How we can ensure a standard refinement procedure even within the independent data model?
Thank you for this nice question. So let me answer first. What is the optimal R factor, the best possible R factor? And as I said before, of course there go some assumptions in that. So if you have a list of observed intensities and the corresponding standard uncertainties, and if these standard uncertainties really accurately describe the variance in the observed intensities, and if this variance in the observed intensities is just solely caused by random fluctuations, not by any other more systematic variations, then you can, from that, calculate this predicted agreement factor. And it's actually quite easy. It's not a big deal, because you will have. Oh, can I go back to the slides? probably, then I can show it again. If we go back to that in the beginning. So the predicted agreement factor, which we have on the right-hand side, you can compare this to the actual outcome from your refinement. So in the counter here, you have just the squared weighted residuals in the counter for the actual outcome. And this is actually what is supposed to be a chi-square sum. And this chi-square sum is, under ideal circumstances, the expectation value for that is the number of observed intensities minus the number of parameters of the model. So this counter on the left side and on the right side are identical from that point of view, that it's an optimum. And then in the denominator, you have the on the left side, the mean squared intensity over the mean squared standard uncertainty, sigma squared. But in sigma also, it may be affected by weighting scheme parameters, so it may be maybe made larger. And on the right, therefore on the right-hand side, you have just the standard uncertainty squared. That's those standard uncertainties in your HKL reflection file. And if they are real, you don't need any. If they are real, you don't need a weighting scheme, and you don't need it for the standard uncertainties. And if there's no systematic error, you also don't need it for your model. So that's a predicted one, and then that's the actual one. So I hope that explains the first part of your question. The second part of the question, how can it be that these are different? That's also an interesting question. I can give you one example where people are usually not aware what shell X is doing. For example, if you don't set your omit parameter S, if you don't set it, it's set to the default value. And in the default value, this leads to the replacement of negative intensities which are more negative than their standard deviation by this standard deviation. So you have the negative intensities are internally modified in shell X for this refinement. And this comes from a wrong notion that intensities must not be too negative, which is just a wrong concept, but it has a lot of popularity in crystallography. No, there must be negative intensity observations if you take all of them into account, and they can extend to whatever range they extend. And if they extend to -3 sigma, it's okay. You would expect that if you just have a large enough data set. But so if you switch from Oleg refine to shell X, you may set this omit value from its default value to a large negative number, like -100 or so. And then you find that the small changes vanish or at least become less. And there may be other things like that. I'm not sure about it. That's one thing I'm aware of, at least.
The next question from Camille. Do you think that the differences between the data quality of various diffractometer vendors can be due to the differences in the data reduction software? For example, Chrysalis Pro versus Apex 4.
Yes, of course. That is. I think there is a influence of the software and how things are treated, but it's just one factor of very many. And the best software doesn't help if the crystal is not centered, for example, properly. And I think, or my impression is that in many standard submissions, it's more the simple things which are not paid attention to, like the centering of the crystal or things like that. And that sometimes people spend more time with correcting for errors which would be avoidable in the first place. For example, by applying a low energy correction procedure instead of using a thin foil which blocks the low energy contamination directly, physically. And that there is a lack of awareness for how important the simple things are. And that if you do the simple things right, then you can go into more details about more advanced stuff, about corrections and so on. But my impression is that this knowledge about how to do proper crystallography is a bit not so much attention paid to. And I see that also from our analysis. When I go through these 310 datasets from IOCR data, I see, for example, a lot of very, very strange scatter plots of observed intensities against calculated intensities, which sometimes are systematically too low or even too large for strong reflections. And that's not like 1 in 100 datasets I'm talking about. I'm more talking about like 10 in 100 or even more, where this is there's so obvious things that kind of catch the attention immediately if you just look at it. But as Saulio said before, that it's probably not, data doesn't get the attention from the reviewers. It's not only with the objective and formal parts, it's also with these parts that, for example, you can have this kind of awkward scattering between observed and calculated intensities without even that this is mentioned somewhere or discussed. So I think that's because there is no culture of openly discussing this. If some of you would start to discuss that, you might end up with your paper being rejected. So from some point of view, it's sometimes better not to discuss things, but we need to get to this point where these things are discussed in order to go deep into all of these topics. I hope that answered the question.
Yeah, Paulina.
Next question or comment is from Piera Maki. The CART system looks like a bit like a quality control in industrial production. There is one very useful tool, which is that of control chart that enable factory managers to appreciate rapidly any out of control state during the production. Is it possible to conceive something similar for X-ray or neutron diffraction data collections? Because data collections period at synchrotron or neutron diffraction facilities are very delicate, and of course, time is limited and granted only after application, etc. Therefore, it would be useful to catch immediately that something is out of control in data collection and correct for the issue if found, instead of detecting problems once back at home after the beam time is gone.
Oh, wow. Yeah, also that would be, of course, very helpful. What we have here at the moment is relies on the final results. So it compares the calculated intensities from your model refinement with the observed one. And so I need to say, no, I don't, or we don't have such a thing, which would be very desirable. That's clear, but it's not with this system which we have here yet. So maybe this will come up at some point, I don't know, but this system is just for the end results to check these and then to look for the errors, also to discuss whether these errors happen, where these errors happened, of course. Did it happen during data acquisition time, or was it with data processing steps, or then with model refinement steps? But to do that, we need to raise the awareness of these errors in the whole community of crystallography and to have all crystallographers working on these topics. And at the moment, I think that's not the case. There are some dedicated groups and some people who have extended knowledge about crystallography, but there's also on a larger group of people, a very large group of people who expect sometimes to have publishable results by pushing a button. And this expectation is also kind of promoted by diffractometer sellers. And the crystallographic background knowledge is getting lost in many cases, so that people don't know what to do if things are not going well. And as long as they go well, it's just publishable, then things are published. But the learning loop about how things are connected here is, I think, a bit lost. And yeah, and that's part of the problem.
Saulius, please ask your question yourself.
Okay, thanks. Yeah, thanks, Julian. Very interesting, very deep insights that you are giving us. And I wonder how much of the quality deterioration in the data come from the crystal properties, because in chemical crystallography, I was taught sometimes you better go to search for better crystal.
Yeah.
Before you start measuring. So how much, and is it possible using your methods to say how much of the data problems come from the crystal itself, high mosaicity, disorder, diffuse scattering, and how much comes from misalignment, contamination of wavelength and such things?
You cannot tell it apart from those cards immediately. What this requires is to apply this method to systematically, and then to learn from that. What it can tell is about disorder, for example. That's taken into account somehow into this, at least in a certain way. Probably not completely, but sometimes it can tell about about the presence of disorder. And the remaining questions is exactly a very, very good question and very profound. I think that's the challenge that the crystallographic community as a whole has to tackle, to put attention to systematic errors, and also to see how much come from bad choices of crystals, for example, or bad centering. And then in this way, eliminate these errors again. So it's kind of going back to the roots and to the simple things and doing them correctly. My assumption is that there is a substantial number of data sets which suffer from that the crystal was probably not chosen very appropriately. But I can't prove that at this stage. It's just a guessing at the moment.
You have bravo from Ella Bartoszak.
Thank you.
And Harry Powell. How useful do you think this might be in diagnosing problems, example, misadjustment with the data collection hardware?
Yeah, I hope that this will be very helpful, but it will also depend on experience. It's not the magic card which is applied and then exactly tells you what's going wrong. But it's more like we need to find out how this grid of criteria is connected to certain errors. So we have seen, for example, that in the 310 data sets from IOCR data, there is a tendency to produce a positively shifted distribution of residuals, which is shifted to positive region. So we could ask for every error which we encounter, from low energy contamination to disorder and twinning and so on. We could ask, how does this affect the mean value of the residuals? Is this shifting to more positive values or more to negative values? And by examining the known errors like twinning or disorder, which then was kind of taken into account, and see how this affects the indicators. We can learn by time to see what happened. And I would expect, of course, in a case like if you have like very, very many red fields, that this may be a problem already at a deeper level, so at a data acquisition or data processing step rather than a model refinement step. But again, that's just guessing at the moment, because this is not widely used at the moment. But we prepare a publication where we have a look at some of these indicators, how they affect twinning, how they affect disorder, and how they affect unaccounted low energy contamination. So that's probably a start where we can.
It's probably the other way around, how twinning is affecting your indicators.
Yes, sorry, yes, of course.
Yeah, we have thanks from Kamil Dziubek for your
question.
answer. And Mike Hayland, it would be perhaps interesting to run this test on some fraudulent structures that were published and subsequently redacted.
Yeah, of course. It's interesting to apply this to all kinds of problems. It also depends, of course, on how this fraudulent structures, how this happened. If they, if this was done in a way as to say invent reflections, which was the case with this Chinese publication, I think it might be that the structure looks like it has an outstanding quality because observed and calculated intensities match very well with each other. So it doesn't necessarily show up a lot of red fields in this case. It depends on how this is done.
Can I comment your this paper you referred to? I mean, we have like a follow-up paper, and you can easily check whether how much your system or how much quality of data is dependent on resolution and the model of electron density refined. Because we published like a follow-up paper to this one you were referring to, and so you can see if you do this for all, as I remember, 700 or even more refinements which were published in that paper. This kind of analysis you can find. Possibly dependence on those two parameters like resolution and model of electron density used. But I'm very much convinced, as we discussed in the past, that the potential of your filter system is I would say, far bigger. That no doubt it can be applied to identify the presence of particular type of systematic errors in the data, and I'm looking forward. I mean, of course, quality of data is very often very sensitive issue. I mean, people, you are showing us how to, I would say, judge the quality of data, but even more important is how to verify what kind of systematic effects are present in the data, and then to have a tool of improving, say, data collection. And I wouldn't say that only systematic errors should be taken care of. Also, random errors should be taken care of. It's a question whether we should analyze estimated standard deviations or sample standard deviations.
Yeah, that's a good topic.
Why not to collect plenty of data set these days when data collection is so fast and almost everybody is having 3-4 diffractometers, so it's really very easy. And at synchrotrons you can collect. It's far more. It takes far more time to prepare sample than to collect data. There is plenty to be done in this field. I mean, I'm very glad that you somehow work in this field and in this field, because that's a very good beginning, but still the very beginning.
Yeah, I agree fully with you, and also with the question about the standard deviations of the observed intensities. And to be frankly with that, I think we have a large problem with the standard deviations, which is not solved for and should have been solved in the last 20 years, but it was not solved. And so we don't have reliable standard deviations for our observed intensities still of today. And that's kind of part of this problem also.
It's even worse. We do not have good quality neutron data to be used for reference. I mean, there are so rare data sets. I mean, maybe it should be a kind of worldwide project to create like a good quality reference data sets.
Actually, it would be very nice to have such quality checks in the database.
Yeah, exactly.
And so everybody who is searching can search also for good quality data only.
That's something we are discussing with IOCR representatives at the moment, whether they can kind of incorporate this into the review process also, so that it's not only afterwards, that when it's already published, then you come up with, oh, but there's something and there's something, but that you can confront authors during the review process. But of course, all of this is kind of tedious, and there are different interests, and it's also a question about funding. And this is an ongoing process, so it's not settled yet, but I would be very happy to see this very widespread and discuss things also with this framework. I would very much appreciate that, yes.
Yeah, we have yet another question from Paul Niklas Ruth. How do you distinguish bad data from good data with an inappropriate or underparameterized model? Example, very high quality and undescribed bonding density.
Okay, if we look at this example, very high quality, I mean, what does this mean in this context? That you have like a charge density data set with high resolution and good quality, and then just apply independent atom model to that. Yeah, okay. So I don't know. You would have to try it probably. How that looks like. It would for sure bring up some features in the residual density, because there's then unexplained density, which makes these shoulders in the fractal dimension plot. So that would be probably an easy way to see that something's not accounted for, and that it's bonding density. But to be a bit more precise about that, we don't judge that the data is good and model is bad or something like that. We just compare observed intensities and calculated intensities. And at this moment, we don't attribute it to one of those two sources, to the model or the observed intensity. We just find these discrepancies between observed and systematic discrepancies between observed and calculated intensities, and know from that, if there is a systematic discrepancy, that there's something not done very well here. It need not mean that the data quality of the observed intensities is bad. It doesn't need to mean that. And Actually, it's the other way around. From the definition of systematic errors in IUCR, according to the IUCR definition, it's always on the side of the model. So even if you have like shadowed reflections and refine them as usual, then the model is wrong in that sense that it didn't realize that this reflections are shadowed, and it should take that into account. It's not like the IUCR definition says these reflections are bad. It's the model that is bad because it doesn't take reality into account, so to say. But that probably goes a bit deep. But we don't judge on the data quality here. We just compare and then see something's not okay. And if you are so lucky that it's just like one card which is not okay, you have a chance to visualize that, to go after it, and probably remove it. And then you learn something, and with this knowledge, you enter the next experiment. And from the next experiment, you may learn something else or something different. So I hope that could answer your question a little bit, at least.
Yes. John Halliwell is writing.
For IUCR, see also.
You've got thanks from Paul Niklas Ruth.
You're welcome.
Yeah, so as we are waiting, yes, John has already written. Paper from 69 in Acta Christ A.
That's about the definition of systematic errors also.
Yes,
right?
that's most people know this. Table 1 error sources in measured F values, random Poisson distribution, the arrival of the quanta in the incident X-ray beam. B, short-term variations in incident X-ray beam flux. C, short-term variations in sensitivity of detection system. Second, systematic.
Yeah, that's just
a differences between measured and actual crystal dimensions. B, incorrect transmission coefficient. C, incorrect extension correction. D, non-monochromatic incident X-ray beam. E, thermal diffuse scattering. F, multiple scattering. G, inhomogeneous crystal specimen. H, radiation damage. I, mechanical misalignment. J, long-term variation in incident beam flux. K, long-term variation in sensitivity of detection system. I'm sure there are far more than this list.
Yeah, absorption correction, for example, can also go wrong.
And John is adding the point being that Schwarzenbach et al. Report emphasize the model, as Julian explained.
Mm-hmm.
Can you comment on this?
I don't get the point I could comment on that. So we have this discrimination between random errors and systematic errors in this list in the top. And of course, the systematic errors can nowadays they can go even further, because we have like unaccounted or unknown entities like the algorithms in the detector electronics and things like that, dark currents and so on. But I don't know what's the question here, which
there's no question. I think it's just a kind of reminder for us for participants.
Mm-hmm.
We see this very fundamental paper published as early as in 69 already.
Yeah. So that's a very good example. This is 69. Like we have a large number of these very nice publications about systematic errors, which goes back to the 60s and 70s. For example, also the normal probability plot is like 50 years old now, but it's not used, it's not fully employed for visualizing systematic errors and then also to go after them. And I attribute this to a lack of a culture which appreciates errors as an opportunity to learn. And I come to these conclusions because I've been publishing so much about systematic errors and just so often get papers rejected by referees who said, well, if you can say that there is an error, you should also say how to remove it. Otherwise, your publication is not of any worth. And I see it, of course, very different. In our perspective is to have a good analysis or a good diagnosis protocol is a worth in itself and powerful in itself. And the application to this is just makes errors visible at first step. And the next step is to look for the cure and the remedy. And this can't be done without the help of the crystallographers, of course. And that's not the aim or the challenge of a group which deals with systematic errors. It's a challenge for the whole crystallographic community.
Yeah, John is adding, it's a comment. Schwarzenbach et al. Cite Abraham's 1969 to ensure they include the perhaps more usual definition of systematic random error.
Yeah, it's important to discriminate.
Yeah. By the way, you showed us this R factor gap at the very beginning for small molecule crystal data. How about macromolecular distribution? I mean,
have you ever computed it to some micromolecular data?
No, I didn't. I would expect it, of course, to be even worse.
Maybe not, because here you show that the R factor is 3 times too large, and if you apply it to, it's hard to predict. Actually, in my opinion, it doesn't have to be much larger.
How about electron diffraction data, the neutron data?
Neutron data, that's kind of
data.
Yeah, it's of course it can be applied to all of this. Somebody has to do it.
Yeah, with electron diffraction and protein data, the problem is that there the standard deviations or your errors of your intensities are even worse. I mean, the quality of this is even worse because you usually have a lower number of reflections of the same kind, so you cannot really compute it from the statistics. So this is like always estimated really from some kind of model.
That's even better. You can do more.
Yeah. So my question actually is, Julian, so have you come to solution what to do if you already knew that your errors of estimated standard deviations for your intensities are wrong?
What do I do about it?
Yes. Or do you have any other indicators still allowing you to check the quality of your feed?
Yes, I mean in this grid of in this grid, there goes also into this goes also whether there are correlations, certain correlations, and so the standard deviations can be reliable, but in most cases they are not. And I think it's the challenge and the aim here to bring the awareness to that, to the community. And that's a long way because the crystallographic community is not aware of that. If, for example, if the standard deviations correlate with the intensity, then the residuals are not anymore random numbers. And the goodness of fit was designed for identically distributed squared Gaussian random numbers.
Exactly.
So what we have, like in 90% or probably 95% of all published data sets, these are not random numbers, and it's easy to show by correlations, significant correlations. That means that the requirement that these are independent, equally distributed random numbers is not met. And of course, it still gives a number for the goodness of fit, but this number is essentially meaningless.
Yeah.
And you can see that. You can see that if you plot, for example, the goodness of fit and then the what I call the alternative goodness of fit. I have a publication, Acta R, about this from 2016 or so, where we give an alternative way to define the goodness of fit, which kind of decouples from these correlations. And if you look at the values you get for the alternative goodness of fit, it spreads out much more than the values from the goodness of fit. The goodness of fit, it's always between, like, in this 310 data sets, it's like between 0.8 and 1.4 or something like that. It's really very narrow. And the alternative goodness of fit is, it can extend to 2 or 3 and to 0.2. So that's part of the problem. And I think that's the main obstacle. And if that's solved, if we know about how to get reliable standard uncertainties, that all crystallographic methods will get a completely new accuracy, or have the potential to get this, and that we can get a lot more out of this method. It will become a very high precision method, but it is not yet, because of these things which are lurking in the background and kind of destroying the statistics and giving us still numbers, but these numbers are quite often just meaningless.
Joseph is asking, could wave function eliminate systematic errors?
Could wave functions eliminate systematic errors? Let me translate this into the following. When I look at data sets where kind of wave functions were applied to, so very kind of professional modern techniques, I don't have an example here, unfortunately, but what I often see is that we have like very good and highly developed models, but the data doesn't conform to that. We have, like, say 4 different models. I remember one model where anharmonic motion and it's not exactly the same question, but it was also like you have like different models with anharmonic motion and, say, relativistic scattering factors, and you look at the differences in order to say which model is better. But then if you use a color card code like this, you see that all of them have several red fields, and they have these fields all in common. And if something changes, it's 1 or 2 of those cards, but the other 10 are still the same. So I think we need to pay more attention first to the general problems with fit data quality, and only if we're sure about that, it's worth trying models that are more advanced, and to look for these differences between these. At the moment, I'm not convinced about that wave functions could eliminate systematic errors, but that may change in the future.
Okay, so let us thank to our both speakers for excellent lectures and really for very good discussion and very fascinating topics, very important topics. I would say fundamental thanks to the whole field of not only quantum crystallography, but crystallography or science in general. So thank you very much.